Now, just as in the volume integrals, sometimes it is more convenient to integrate on the y-axis than it is to integrate on the x-axis. So let's suppose that I have a curve given by x equals, let's call it g of y. I can do all of that business setting up the Riemann sum again. And to be honest, that's not a practical idea. That's just telling us how to find the formula. So let's skip some of that sketch work and go ahead and say that my arc length formula is going to look like this. The length L is going to be the integral. Now from y equals lower bound c up to y equals upper bound d, we are integrating the square root of quantity 1 plus g prime of y squared dy. Again, this square root of 1 plus something squared, this is the hypotenuse formula. This is what happened to the lengths of those line segments while I did the limit of the Riemann sums. So again, you can always bring it back to the geometry and here the hypotenuse, the same way as my volume integrals always let me pull out area, width, length, multiply those things together, I get volume. Let's continue. Let's do something explicit. Find the length of the arc of the parabola y squared equals x from coordinates 0, 0 to coordinate 1, 1. All right. So if my x is equal to y squared, I need to calculate a derivative. And my derivative is going to have the Leibniz notation dx on dy. Well, you know, it's just power rule. It's just 2 times y. That's fine. What are the endpoints for my integral? Well, those are going to be y equals 0 and y equals 1. So this integral for the arc length will be the integral from y equals 0 up to y equals 1. My integrand is the square root of quantity 1 plus dx on dy squared, all dy. Well, isn't that something? Let's go ahead and use the formula. dx on dy is 2y for this problem. So this must be the integral from 0 to 1 of quantity, of the square root of the quantity 1 plus 4y squared. Remember, I have to square that derivative. All dy. Can I do that? Can I integrate that? Can I use a u substitution? What am I going to do there? Oh, right. Trigonometric substitution. That exists. This is why we didn't do arc length until after the trig chapter. So what's bringing me down? I've got a square root of 1 plus 4y squared. Okay, well, I need to get rid of 1 plus something squared out of a square root. I'm going to go with the tangent function because I know that I can use my 1 plus tangent squared equals secant squared, right? Got to keep that fresh in our memories. For this one in particular, we're going to go with y equals 1/2 the tangent of theta. And when I do my exchange rate for my differentials, I find that a dy is worth 1/2 of a secant squared theta, d theta. So this integrand root of the quantity 1 plus 4y squared. Why, that must be the square root of the quantity 1 plus tangent squared of theta. Well, 1 plus tangent squared of theta is secant squared of theta. And if I'm going to take the square root of secant squared of theta, I had better get a secant of theta. Well, cool. That's looking good. What does my integral look like? Well, I got to change my bounds. If y equals 0, then the tangent of theta has to be 0, and theta equals 0 gets me there. That's looking good. For my upper bound, if y equals 1, then tangent of theta has to be equal to 2, right? Because y is a half of the tangent. So theta is going to be the tangent inverse of 2, or I might call that the arctangent of 2. For right now, let's just call that angle measure alpha. We'll get back to that. Okay, here we go. So my arc length is now equal to the integral from 0 up to alpha. Again, we'll figure this out. The integrand is secant cubed of theta d theta. And we pulled out that 1/2 over here. Well, when I go to take my antiderivative, after a little bit of work here, the antiderivative is going to be secant of theta, tangent of theta, plus the natural log of the absolute value of quantity secant of theta plus tangent of theta. And these we have to evaluate at the coordinates alpha and 0. Well, I already know that my tangent of 0 is 0, so part of that goes away. And my fundamental theorem of calculus step, I say, well, I've just got a quarter of secant of alpha, tangent of alpha, plus natural log of secant alpha plus tangent alpha, like that. Okay. This is why I did not calculate an explicit value for alpha, because I already know that tangent of alpha is 2. So this tangent of alpha is 2. And this tangent of alpha is 2. All right. Well, can I figure out the secant there? Well, secant squared of alpha is 1 plus tangent squared of alpha. That's just 5. So secant of alpha is the square root of 5. Let's go back to that formula one more time, real quick. I've got a quarter of the square root of 5 times 2. And the natural log of the square root of 5 plus 2. Hey, nice, nice. I didn't actually need to find my angle measure. I just had to do a little bit of thinking. So for this problem, the arc length has an exact formula of square root of 5 on 2 plus the natural log of quantity square root of 5 plus 2, all divided by 4.